All right. Good morning. Good morning. Let's go ahead and get started with getting your exponent lesson done today. So, first and foremost, what I'm looking at here is going to be the same notes that you guys are looking at. Okay? Exponents are able to be expanded. You know how, like, when you have addition, if you have 2 plus 2 plus 2 plus 2, that's the same as saying 2 times 4. Exponents work the exact same way, but these are going to be in terms of multiplications instead of in additions. Okay? So if you look really closely up here, 3 to the 4, instead of adding 3, we're multiplying 3 4 times. And if I look at the x to the 6, how many times are we going to multiply the x? 6 times. Sometimes it's easier to think about these exponents as expansions like that, and then to count those x's afterwards. It does help us to keep track of them, especially as we start getting into some of these complex properties and such like that. All right, so I want to go ahead and go through the rules. I'm going to highlight some of the key parts and how to create these expansions and how these expansions might help us understand some of the properties that I was trying to explain over the past 2 days. Now, the first thing I wanted to look at, the first rule that was going to be the most help to you, was going to be an exponent being applied only to the base that the exponent is actually attached to. You'll notice that on that first example right there, that you have 2x cubed. X raised to that third power is called cubed because of cubes being three-dimensional shapes and this being a power of 3. You're going to see that when I expand it, there are 3 x's and 1 2. That's because it's only the x that is being raised to the third power. Okay? If you put the stuff into the parentheses, this 3x is in the parentheses, that whole thing there is being raised to the 4th power. That means that everything in there you get 4 copies of. That's where you get the 4 3s and the 4 x's. Now, no. You can simplify that a little bit. If you think about 3 times 3 times 3 times 3, you would be able to do literally 3 times 3 is 9, times 3 is 27, times 3 again is 81. That's going to be what 3 to the 4th equals. And so we could almost think of this, and we will think of this, as 81 with x to the 4th power, because of us being able to multiply those 3's together and actually get a whole number, an actual number at the end of it. And then, of course, the x raised to the 4th power to show that there are 4 x's being multiplied together. Okay? From there, I want to talk about rules 2, 3, 4. Okay? Rule number 2 here. When the exponent is inside the parentheses and also on the outside, what I mean by that is if I look at this 3 and the 4 up here, you can expand the inside of the parentheses first and then re-expand the outside of the parentheses there. So if you look really carefully, 2x to the 3rd power, it's the x to the 3rd power here that got expanded to where you had x being written 3 times. Okay? Literally x to the 3 x's. Then when you see that being raised to the 4th power, you'll see how you get 2x to the 3rd, 2x, blah, 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 blah. You get that copied 4 different times to show the 4th exponent on the outside there being applied. From there, you can start grouping stuff together. You'll notice you have 4 2's put together right here. You'll notice 2 times 2 times 2 times 2 is 16. 2 times 2 is 4. Times 2 again is 8. Times 2 again is 16. And then if you look super duper carefully, you have a bunch of x's right here. There are 12 x's. That's where the 16x to the 12th comes from, because we're multiplying all those x's together and all those 2 together. Dividing with exponents removes some of the things that are being multiplied. You'll notice x to the 4. I got 4 x's here. I have y to the 3, and I have 3. Well, there should be 3. Oh, It's because it went over more. I have 3 y's there. When I divide it, I've also got 2 x's down here and the 1 y right here. If I try to divide those, since dividing is the opposite of multiplying, when I said last time about us canceling those out, it's because division is the opposite of multiplication. I can literally go, those y's are going to cross out. These x's are going to cross out because there's 2 x's being divided by 2 x's and 1 y being divided by 1 y. That leaves us with, you'll notice, 2 x's being multiplied and 2 y's being multiplied. And since we're multiplying 2 x's, it is x raised to the second power. Same with the y's. There's 2 y's being multiplied, so that is y raised to the second power as well. That's where that comes from. Number 4, negative exponents are going to flip the base, and it attaches to the opposite side of the fraction. And then the exponent outside of a fraction is also applied to the top and the bottom equally. This applies specifically to fractional situations here on both of these. Okay. 4x squared and 5y cubed, you'll notice that the x squares over here, x squared, x, there's 2 x's there. Same with the y3, y to the third, you got 3 y's here. Then it gets squared, and just like we did here, we go ahead and compress those together where all those y's go together to make 6 y's. And you have the 4 x's being combined together. That's where the x to the 4 comes from. 4 times 4 is 16. 25 times y is 6. The negative exponents are going to be what shows up when you have something like, and I would write this down, x to the negative 3. That's where the x flips to the bottom side of a fraction, and you get, 1 over x raised to that third power there. Okay, it goes from being x to the negative 3 on top to x to the negative 3 on bottom. And that applies throughout the entire fraction. The last couple of things I want to talk about is 1, anything raised to the 0th power is 1. And also I want to do some examples with you. Now, to me, I tend to work better when it comes to these exponents as following the rules without needing the expansions. But I'm going to do my best to do these expansions with you real quick. Let's start by expanding out what's inside these parentheses. 2 times x times x times y times y times y. I got that because of the x to the 2 and the y's to the 3's. Okay? The y's to the 3's gives me those 3 y's. I have that happening to it twice. That means that I have my second time here, 2x, x, y, y, y. When I combine those together, 2 times 2 is 4. There's 4 x's here, so x to the 4, y to the 6. Remember that rule I told you about yesterday, powers raised to powers, you multiply those exponents? It shows you that 3 times 2 is 6, and that's why you're listing out 3 y's being multiplied 2 times. You're listing out 2 x's being multiplied 2 times, okay? So do at least remember that those rules exist as shortcuts. But if you forget these rules, like, there's nothing wrong with doing expansions on this, okay? The one next to it is not super duper hard either. We can start by just looking at the numbers that are in front and thinking about those first, the negative 48 and the negative 8. When you divide those, you get a positive 6. If you think about it, the C2, CC over C to the 1, you could even write it like that, CC over C. Those will cancel. You'll just get the letter C right there. That takes care of these C's that we just looked at. I mean, the same thing would happen with the D's too. There's 4 of them. 1, 2, 3, 4. Over one of them, D. Okay, those are gone. D to the 3rd power, D3. That's where we get this from, is by taking those and dividing them and having it cancel. And when you think about it canceling like that, it's like if you were to say 2 times 2 times 2 divided by 2. That last times 2 divided by 2 would cancel itself out because it would just be like doing the opposite, and it would put it back to just being 2 times 2. 2 times 2 is 4, times 2 is 8. Divide that back by 2 puts you back to 4. That's kind of the rule we're following here. On that next one over, 6x0y8 minus 2y2 squared, to the fourth power. That's going to take a little bit more for us to be able to expand out. The good news is that the 6 stays the same with just the 6. X to the 0, you're going to note, is 1, and 1 times 6 is 6. From there, we can just look at the y's that are next to it. There's 8 y's there, and I'm a little bit lazy to have all those written out. When it says that you're going to subtract that, okay, you can only subtract these if the y8s match. Like literally, it has to be y to the 8th power. And when I look at this next section, it doesn't show anything about y to the 8th. But I can distribute that negative into that negative 2, and I can go, oh, minus 2. Y to the 2 raised to that 4, you're going to have 2 y's listed 4 times for a total of 8 y's. That means that, yes, the y's to the 8 still match up, which means you're going to end up with 4, because 6 minus 2 is 4, y to the 8. Since we are adding and subtracting, as long as the bases completely match, you are good to go doing that. This fraction over here at the end, 3m squared n to the 7th m, yeah, you get the idea. If you really think about it, you could distribute this exponent in. Think about it, 3. How many times are we going to write that 3? 5 times. I'll take that 3 and I'll raise it to the 5. That m, in the inside of the parentheses, I'm going to list it 2 times. Then I'm going to list those 2 m's 5 more times for a total of 10 times that my m is going to be written. Same happens with the n. It's going to get written 7 times, and then those 7 n's would be written 5 more times, telling me that we're going to be looking at a total of 35 n's. Okay, that's going to be where I'm getting this n to the 35 from. When I put that over, it's going to be another m right here, and that m is written by itself, but it also gets that 5 applied to that. So I have m to the 5. And when I say, again, we're canceling out that denominator there. We're able to divide 10 m's 5 times out. That means that when those cancel, and again, this is a 5, when I write this out, the 3 to the 5 doesn't change. You're just going to get 3 raised to the 5th. M 10 times, divide out 5 of those. It's going to undo 5 of those 10 m multiplications. So m to the 5 happens there. The n part, n to the 35, that doesn't change. It still stays as 35 because there's no other n's to divide out. Like, that's it. The next thing I'm looking at here is the 6 and the 3. If I look at the 6 and the 3, they are being multiplied. 6 times 3 is 18. I can take my x's now, 5 x's, and 5 more x's, and 0 more x's. 5 x's times another 5 x's, x, 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 x. And again, x, 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 x. That would give me 10 x's being multiplied. That's where the x to the 10 comes from that I'm writing right here. And remember how I told you guys that anything raised to the 0th power equals 1? That x to the 10, if this x to the 0 equals 1, that would just be like saying 18 times 1 is just 18. Like, I don't need to think about it again. It's just staying that same number. That's what the answer here is, 18x to the 10. The last one I'm looking at is the fraction. I'm going to, again, look at the coefficients first, these 22 and 2. And when I divide those, 22 divided by 2, I get 11. My y's, y's are interesting. I got 6 of them on top, and I'm dividing one of those 6 out on the bottom. 6 take away that 1 on the bottom gives me a total of y to the 5. And again, that negative exponent that we're looking at on the z is going to be interesting for us. Whenever we have that negative exponent, we switch it from negative to positive and bring it across to the top. When we do that, that doesn't just leave us with the 8 z's we started with on top. Those negative 7 z's, when they switch to positive and go to the top, increase that count from 8 z's to 15 z's. And that's why I'm going to get z to the 15 here. If it helps you literally to write out y, and you put that over another y, and you go, oh, look, I can cancel that out, and just count 1, 2, 3, 4, 5 y's in order to get that y there. Do the same thing with the z's to get the 15s. Like, it's okay to do that. That's kind of what expansion does, is it allows you to rewrite it in longer terms and then be able to work with each of the individual pieces within those longer tools to help make sense of it. Like, that's why I'm showing this to you as a way to visualize it, as well as to give you another option when it comes to solving this. There's nothing wrong with taking your time and answering these questions in long form on the star. Like, do what you got to do to get it right. I'm going to go ahead and make sure that you guys are doing okay. If you have any questions, don't be afraid to throw your hand up. The other classes are going to be doing easy sauce work, like no big deal. So just throw your hand up. I'd be happy to come over and help you out. Don't be afraid to stop me and ask me, all right?